Otherwise, there's jokes about forgetting to press record instead of yeah. So so hello everyone. Yeah. So today we'll talk about Green's theorem in a vector form. And so we have formulated Green's theorem in this way before. So it's an integral over the set D of q partial derivative of q over x minus p minus partial derivative of p over y dx dy, and that's equal to the line integral of a closed path, which is the boundary of the set D of p dx plus q dy, or it's this, we can write it as the dot product, right? So it's integral of f dr over the boundary, and the left-hand side, the integrand of the left-hand side is reminiscent to the expression we saw before, namely when we calculate the curl of the vector field f. So let's see how this comes about. So the curl is calculated by evaluating the determinant. And now for sort of, since vector field here is two-dimensional. Okay, I don't know what happened. It says that sharing has stopped abruptly. Let's try it again. Interesting. Just the overflow of the network, or let's see. Okay, let me leave and then join. Ask any questions while I'm fixing this. Yeah, I'm gonna try it one more time. I'm just. Yeah, there we go. So, so far vector field has two components. Well, how do we write it as a vector field with three components? Well, we'll complete it with 0. This way we think of it as a, it's a plane, and yeah, so stuff goes on the plane. There's some curve here. There's a vector field which is defined on the boundary, and then we treat it as if it's a vector field in 3 dimensions, only that it has a its third component is equal to 0. So we embed the xy plane into 3 dimensions. So this way, curl f will be a vector that is perpendicular to the plane. Right. So what curl is? It's this, right? So everything is 0 except the last component. So it's a vector with components 0, 0, and then qx minus py. right? And then remember that when we talked about areas, then I mentioned that well, one can think of an area as a vector, right? So if you have so at least the small part of this element dx plus dy. Like yesterday we had an office hours, which I think I also forgot to report. But anyway, one of the questions was what's the geometric meaning of this wedge product dx dy, and then well, there are many answers to this, and one of them is that it provides you orientation of the area, right? So of the little area. So say you have this little little patch of the set, which is between two vectors, dx and dy, right? And then you would if you order it like this, to dx goes first using the right-hand rule, right, and dy goes second, then you can assign a direction, right, to this area of this small patch, dA, which is now a vector, right? Which is you can simply think about it as k, which is the third vector, times dA, right? And if you take this vector dA and then take a dot product with this curl, you'll get a scalar quantity, which is exactly what we need for the integrand on the left-hand side, right? So therefore, the left-hand side can be rewritten as integral over d curl f dot dA, right? Because yes, and this way vector dA, well, the vector has components 0, 0, and dA. So that's the left-hand side, and the right-hand side does not change, right? It's the same. So it's the contour integral over dr over the boundary. Yeah. So this is the formula in the vector form. Okay. Any questions? All right. Now so one more comment here. So we have so this when we have this integral, we have let's draw this domain set D again. So this is the boundary. Right, and then let's look more carefully about the what's going on here. So the vector field F is defined everywhere, in particular at every point on the boundary, right? And the left-hand side here calculates the line integral over the tangential component of the of this vector field, right? So when we calculate this dot product with dr, right, what we're effectively doing, we calculating the projection of the vector field on the tangent line, on the tangent vector at each point, right, and then integrating it over the path. But we can ask ourselves, what will happen if we calculate the normal projection here? Okay, so at every point, we can decompose the vector field f into this so into the normal projection and the parallel projection. And the parallel component, right? So the parallel component is taken care of here in this formula, right? But now, how about the normal component? So what will happen if you integrate over the boundary this normal component, right? So just to reiterate, so because of the scalar product thing, you can write it as a integral of the boundary of the parallel component ds. Right? That's what the scalar. That's what happens if you compute the scalar product. Right. Now the the physical interpretation of the second integral is the following. So it will be related to the flux. It's called the flux of the vector field f through the boundary. So here's another picture for it. So there's a boundary, and then imagine, so the most clean example is the charge inside. So there's an electric charge Q, right? It's a positive charge, and so we live on the plane, and then there's a electric field lines that emanate from it. So that's so they go radially, right? At every point, they go radially away from the source, from the center, from where the charge goes, right? So that's that's field F, right? And then we can decompose F into the tangential components and null components. Right, so if you only look at the normal component, that would, that's the definition of the flux, right? So it's in a sense, the meaning of the flux is that it's amount of, well, it measures the amount of sort of field lines, right, that go through the boundary. So here we give a two-dimensional example, but of course, similar formula exists in higher dimensions as well, right? So I mentioned to you that there's an analog of the Stokes of the Green's formula in 3 dimensions. Sometimes it's called Ostrogradsky-Gauss formula, but we'll know that it all comes from the same Stokes formula if you write it in differential forms, right? So basically, think of it this way: you put a point charge of some, or not necessarily point charge, basically some source of field where this field lines start, right? So this way, all field lines they go through the boundary, right? And then you would calculate the flux. And so we'll get to this calculation in a second. But before we go, let's look at a couple of qualitatively different pictures. To say again, there's a domain D, and then field lines go like this. Sort of, they pass through it. And so, well, I throw this from field line, but it's more it's a trajectory where so that the vector field is tangential to this line at every point. And so, in particular, here f goes like this, right, and here it goes inside. Right, and you can ask, and sort of inside there are no sources, right? So every field line will go in, and it will go out, right? So it would be reasonable to assume that the flux here in this situation. Oh, okay, this should not. Yeah. So there's no vector over here because we already projected it out. Yeah, so let's derive the formula. So in other words, we want to derive the formula, which will be so that's the right-hand side or left-hand side of this new formula, and the other side should tell us what's going on inside of this set, right? It would be some two-dimensional integral over this set D, which should tell us something about what's going on inside, right? Whether it has charges or it doesn't. And so let's use the rules of vector calculus to transform this expression. I'm going to rewrite the formula. I'm just going to move the page a little bit. Okay, so this integral of f perp ds over this boundary, we can write as a dot product of f with the normal vector ds and the, now we can switch to some parameterization. Let's say the curve is parameterized, so that let's say this the boundary is parameterized by some curve. Well, yeah, so the boundary itself is a curve, smooth curve, which maps from AB to R2. And such it's a closed loop, like so the value of the function is the same at the endpoint. But parametrically they're different points, right? So then we have f dot n of t, and then ds is absolute value of r prime dt. And so that's the integral. Okay, now we know what the so now we need to write down f. So f we know what f is. So f is a vector field P and Q. We don't have to worry about z direction anymore. So it's a two-dimensional field. Now the tangent vector is the derivative, right? So it's so the unit tangent vector, right? So it's the normalized vector of the derivative, right? Or it will have components x prime, y prime divided by absolute value of r prime. And then the normal vector will be perpendicular to it, right? So the unit normal vector, which what we denoted with a little n here, will have, we'll have components n equals, so it should be orthogonal, so we can write it as y prime negative x prime. So we're picking this direction, so it will be a vector that corresponds to rotation by 90 degrees of the tangent vector, right? Divided by the same norm. Okay, So that's the normal vector. If you forgot, let's draw the picture again. So we have tangent vector here, and then normal vector there. Okay, and now we need to take the dot product of f and n and plug it into the formula, so we get this integral from a to b. So it's p times y prime minus q times x prime divided by r prime of t absolute value multiplied by r prime t absolute value dt. Right, which is equal to what? It's equal to integral from a to b. This thing cancels. Yes, we have p also of x of t, y of t, y prime of t, dt minus q of x of t. So let's just write everything complete. X prime of t dt. And now let's combine it back into a differential form. In terms of using differentials, it's also equal to integral over this boundary of the vector field p dy minus q dx. Right? Or we can say that this is a new vector field. Let's call it hdr over the boundary, where h has components negative q and p. Right, so see, it looks very familiar. So it's the negated y component and x component, same way as the normal vector here behaves. And now we can apply Green's formula for vector field H. Right, so what does Green's formula say? It says that you take so that this guy is equal to double integral over d of the x derivative of its y component, which is p, minus y derivative of its x component, which is negative qy. Dx dy, right? Or it's equal to, well, forget about the minus, it's equal to px plus qy dx dy. Okay, so far so good. And well, you can see here that's what stands inside the integrand is the gradient of f. And the gradient is divergence of f. It's the dot product of the gradient with the vector field f. The divergence of f dA. Here dA is a scalar. dA. Okay. So to summarize, we have proven the following formula, which says that the flux, right? So flux over the the boundary of set D is equal to the integral of divergence of this vector field over D. Yeah. What is H again? H is this new vector field here. So so we got to this line, integral over the boundary p dy minus q dx, right? And I want to interpret this as a contour integral of a vector field, right? It's not f anymore, right? So so it's this vector field here. So see here, q negative q multiplies x component, and p multiplies what? So you have negative q dx plus p dy, right? So it's as if we have this other vector field h with components negative q and p, which we're integrating over the boundary, and we're applying the Green's formula to that vector field. Yeah. So coming back to electrodynamics, to our favorite electricity, this is well, if you use this is one of the it's one of the Maxwell's equations, which describes electrodynamics. So here, so the left hand side is flux. Yeah, so like it's like flux through the boundary. And the right-hand side is the integral of the charge density. Which is the charge itself. Right, so we'll look at an example yesterday, and I mentioned to you, so if we have a point charge, right, and say, we had a three-dimensional example, but anyhow, so I'll write the 3D formula in a moment. So we have the charge and then the field, electric field, which goes away from this charge. So the divergence of that thing was equal to 0 everywhere except at the origin, where, well, we should, I told you and asked you to take my word for it, there should be a delta function. So it's a distribution which is singular. So it has only, everything is supported at one point at the origin. So if you integrate that over space, or in this case, over the plane, we'll get the charge. Yeah, so one of the Maxwell's equations reads, use this color. One of the Maxwell's equations it says that the divergence of the electric field, right, is equal to the charge density. Yeah. So that's the kind of, it plays a role in the left-hand side equation. And then the sort of physics interpretation of the first equation here of the Stokes theorem, excuse me, of this formula of the Green's theorem in differential form, right? It would tell you that the so now we're talking about magnetic field, right? And the so what they tell you is that if you have a current that flows on the boundary, right, then it creates magnetic field in space, right, which sort of goes like this, right? So say here, say red arrow shows the direction of the current, right, and that would create magnetic field It will go like this, right? Through the loop. Right. Then it would relate the curl of the so the magnetic field, which is curl of the vector potential. So if F is this vector potential whose curl is equal to the magnetic field, then it gives you it shows you that the magnetic field is equal to is related to the circulation of a current, right? So integral on the right hand side will give you the it will be related to the current that goes along the boundary, and the left hand side is the magnetic field. Yeah. Okay. Questions? Just for completeness, let me write you down Maxwell's equation. There are 4 of them. Right. So this is what that's the first one we already have. Right. It's this. I will write them in differential law and then in terms of the fluxes. Right. So divergence E is equal to rho. Then divergence B, if you have a magnetic field, divergence of B is equal to 0. That's sort of the second equation. It tells us that there are no magnetic charges, right? So you cannot sort of make this interpretation. I don't know what's going on. Somehow the broadcast dropped for the second time. Okay, should not. I'm not sure whose problem is this. I just need to reset my tablet. Okay, we don't have much time. Let me just show it to you in the web page. Right, so here they are. So the that's the first equation. So they're written in this so-called CGS system, which has epsilon 0. But let's say it's not there. Let's say we're doing the so it's an SI system where there's in CGS there is no epsilon, right? So that's the divergence of E is equal to the charge density. Divergence of B is equal to 0, and then there are 2 more equations which are related to time dependence, right? So let's start with the previous one. So that's the equation that we had. It's the first equation. Now I want to annotate on this thing. Why can't I do that? I can annotate here. Okay, so that is related to, well, this integral that we had before. It's the integral over space of divergence E, right, is equal to, it's actually written here, right? So the, I can just show, yeah, I can just show it here. So now here they're written for 3 dimensions, and then there's a straightforward generalization of what we did for 3 dimensions, right? So now think that you have the vector field E, right, in 3 dimensions, and then its flux will be integral over the boundary, which is the area. So here S is the area, is the surface area of that sphere, if you like, that surrounds the charge. So the flux of the electric field through this surface is equal to the volume integral of the charge density. Okay, and then if you sort of look at integrands, right, it's the same as the divergence E is equal to the charge density. Okay, and second equation talked about this before is that if you have a magnetic field and if you integrate, well, we did the two-dimensional version. But if you integrate it over the surface, it has to be 0, meaning that there are no magnetic charge density. There is no magnetic charge density. There are no magnetic charges, well, at least of this moment. We have not discovered magnetic monopoles yet. So that would tell you that the divergence of B vanishes. Now, the last equation, let's look at the last equation first. So it's ignore this term with time derivative for a second. So let's say there's no, there's nothing, the time does not change. Say we have, so let's say this guy is not here. Only focus on this thing, right? So that's the equation that we already have. So if you replace in our notes, right? So if you replace vector field, so if B, I remind you, so B was equal to, yeah, so B is a curl of this vector potential here, right? So we have an integral, circulation integral of B, and that's equal to the area integral of the current, right? So it's the current density. Right, it's like it's the current that goes through, and then if you write this in terms of differentials, you get a curl B, right, is equal to the current density. Okay. So yeah, so we have seen a realization of these three equations, and the fourth equation. So if you include time dependence, if the magnetic electric field change with time, right, then there is this third equation, which is the electromagnetic induction, right? It shows you the curl E, right, is equal to minus the rate of change of the magnetic field. Yeah. So if you have a magnetic field that goes through the loop, and then it generates the current that goes around the loop, right? It's described by this equation, and then finally there's a fourth equation which sort of which gives the correction, this correction here, which is called the displacement current. It's a correction to the, yes, so the curl B is equal to J, the current density, and then there is this correction due to the change of electric field. Yeah. So they look almost symmetric if you replace magnetic and electric fields. Well, except that there are no magnetic charges, and the displacement current only appears in one of the equations. Yeah. So we have discussed geometry behind Maxwell's equations, and yeah. So it's a beautiful story, which was discovered about 150, well, 160 years ago. I think it's 1864 or something like that. Okay, I think I should let you do the test. Are there any questions about the lecture? Quiz will cover chapter 15, the last week's materials. Yeah. So we have completed 16.5, and then we'll talk about parametric surfaces and their areas on Friday. We'll do some practice, yeah, and we'll talk about areas of surfaces. 16.6, and yeah, there's this topic, and also orientation. Yeah, we'll talk about that. Yes, and then there's all this. So yeah, I think we'll do some discussion on Friday, and then a little bit more lecturing on Monday. Okay. Great. So then I think we should adjourn today, and then I'll see you guys tomorrow. Thank you. Bye.